I have everything here on my own personal video and the one from the university, but in theory, this new video that you access here from modules should have the screen and also an inset with what we're seeing through this camera, which is going to be mostly myself. But it should be better quality, so we'll see. We'll see if this works. I'll still keep uploading my videos on YouTube, but this is going to be a second option for you, okay? And eventually, if this works well, then I'll download these videos from here, and I also will put them in YouTube. But we'll see how it goes. For now, I'll just continue with the same system. Okay. Today, we're going to start talking about hydraulic fractures. Probably, for now, this is the most important application that we're going to see out of this class. We already saw stability of faults, stability of wellbores, and now we're going to talk about hydraulic fracturing. The first thing I'd like to say about hydraulic fractures is that hydraulic fracture is something that we already have in nature. They happen naturally in the subsurface, and sometimes it depends what is the type of fluid that makes the hydraulic fracture. But these natural hydraulic fractures, those are called dikes. They are spelled with this I or with Y, with I or with Y. It depends, same explanation. Some people are laughing, but that's why how they're called. And there are basically two types of natural hydraulic fractures that we find. And they are hydraulic fracture caused by magmatic fluids. Sometimes when you have a magma which is at high pressure, and of course at high temperature in this case, if the pressure of the magma is higher than the minimum total stress, is going to literally open up the earth and flow to the surface. And what you see over here in this diagram is what you see on the right. And here, in this case, this is the hydraulic fracture, and this would be a plane which is coming out of the screen into this direction. I hope you can also see, we'll make a zoom, how it gets thinner towards the top. So that means it's propagating from the bottom upward. And in this case, and in that case over there, this would be a type of hydraulic fracture which is magma. Once the magma cools down and solidifies, what you have is this field, this fracture field with the magma, and now solidified as a rock. And what you see in this other image is on the bottom left is what you will see on surface, how the dikes, sometimes they get to the surface, and if you had some erosion of this region, then you will just find the most resistant part of the rock, which in this case will be the magma, and this will appear like this wall of magmatic rock on surface. This is in New Mexico. If you ever travel to New Mexico, this is called, what was the name of this? Shiprock. Shiprock in New Mexico. If you go around there, these are magmatic dikes. And you, for scale, you can see there is a house over there. So this can be pretty large and pretty tall. Usually you will have those close to a volcano. And again, that would be just an eruption of magma. I hope you notice sometimes here that there are parts of this magma that is not like a vertical fracture, but it's more like a horizontal plane. Those are called sills, and that happens when do you think that will happen? You have now a hydraulic fracture, which is a vertical plane, and then at some point it might turn and go into a horizontal plane.
Sure.
Sorry?
What is the low permeability zone?
Well, for the magma, almost everything is low permeability. It's very likely it's not going to get into the pores of rock, even if they are large. Probably this one is a little bit clearer. Why do you think this will turn and start growing now horizontally? We're going to see that there might be two reasons for this. The principal one is a change of the state of stress. It might happen that because of the different properties of these layers, the horizontal stress may be larger in this carbonate rock than in here. So when it gets to there, it finds that the minimum principal stress is now vertical, and it prefers to open up, pushing up the rock rather than pushing it to the sides. And that's because we have a change of stress regime, and here we go to either normal faulting or strike slip to reverse faulting. And that sometimes can be also helped by a change in the properties of the rock. Some rocks are harder to fracture than others, and if at that point the pressure is not enough to continue propagating in this direction up, it may continue in this direction until it finds enough pressure to go up. Okay, let me see if I forget anything. So these are, remember, natural hydraulic fractures. There is one more type of natural hydraulic fracture, which is a sedimentary hydraulic fracture, in which we can find some formations that they have such a high pore pressure, and they may have events of high pore pressure that the pore pressure gets to the value of the minimum principal stress, and the sediment, this especially happens with sands, it behaves as a quicksand. It's not like a solid anymore, it's like a quicksand, and it can flow similar to magma, and that forms, instead of these magmatic dikes and sills, it forms sedimentary dikes and sills. And it's a similar thing, but you will have strata of rocks being fractured by fluidized sands, forming these same type of structures. This is very important because in some locations, these, particularly the sedimentary dikes, they can be leaks for hydrocarbons to go directly up to the surface. And there is another type of those, similar to those structures, which are called chimneys, that are very similar too, in which you can have a very high permeability channel that goes directly into the surface. Okay, but the most important part from here is that you remember that we have hydraulic fractures that we can do in petroleum engineering, but also there are hydraulic fractures in nature. Okay, so let me get out of here. Let me initiate the dog camera, and we'll go to the next topic. No. Okay, so today we start talking about hydraulic fracturing, and the first topic is fluid-driven hydraulic fractures in nature. We just call it fractures. Fluid-driven hydraulics is the same thing. For this one, we said that these are going to be considered by magma, or fluidized sediments. Which means something similar to quicksand. Both of those can form dikes and sills. Okay. Before we get into talking about hydraulic fracturing for completion, we'll talk about hydraulic fractures in petroleum industry for drilling and also for injection of fluids. When do you think petroleum engineers started to do hydraulic fractures? How many years ago, or in which year?
1960.
Around there, yeah, I think it's something like around 54, 56, you have the first type of explanation of how hydraulic fractures happen in nature. So they're pretty old. I mean, it's been like more than 60 years that hydraulic fractures are used in petroleum engineering. And we'll start talking, continuing what we were talking in wellbore stability with hydraulic fractures in well testing and during drilling. And first, we'll talk about the leak-off test, which is done for drilling. Let me turn this off. Okay. All right. So we have seen how we find lower bounds and upper bounds for wellbore stability. For those, one of the principal variables is minimum principal stress. We utilize the minimum principal stress, or SH mean, for everything, because your breakdown pressure is going to depend on that. The pressure at which you have breakouts is going to depend on those stresses. That's going to affect stress anisotropy, and that's going to be a very important value for wellbore stability, and especially for the upper bound. Well, this value you have to get it somehow from some other type of information. And one of those tests that is going to give you that information is going to be the leak-off test. The leak-off test, what is done is you get to drill up to a given depth, after which you lower the casing, not to the very bottom, but just leave a section. You cement, or you may previously cement your casing, and then you inject drilling mud, because this is going to be full of drilling mud, in this sort of closed container. Well, remember, this is, I mean, it's not that close. This is a rock. And here, by injecting mud into this section, we're going to be able to change the pressure, because here we put a packer, and we can control the pressure inside this volume. Okay, let's calculate what would be the breakdown pressure for this wellbore, because that's our objective. Our objective is actually to measure the breakdown pressure, but with the equations that we know, let's try to calculate that. And for this, let's assume normal faulting, and of course, you know very well by now that for normal faulting this is going to be the case. And we're going to further assume, to make our equations a little bit simpler, that SH max is going to be the same as SH min, and I'm just going to call it SH. And if I subtract pore pressure, it's going to be sigma H. If you remember the equations for breakdown pressure, the breakdown pressure was equal to the pore pressure plus 3 times the minimum effective horizontal stress minus the maximum effective horizontal stress plus the tensile strength of the rock. And for this case, we have made this equation a little bit easier, since we are going to assume that these two are going to be the same. This is just going to be PP plus 2 times sigma H plus TS. That's the theoretical breakdown pressure of this well. And we'll utilize this equation to see how that is going to affect the response of a leak-off test. Okay, so here we go with the leak-off test. In the leak-off test, what we're going to do is we're going to inject drilling mud into this open hole section of the wellbore under closed conditions. So we're just injecting, nothing gets out. In theory, or ideally, through the this should be cemented, so nothing should get out or escape from this cavity. So here we're going to have injection rate, and at the beginning this is going to be 0, then it will increase, we'll keep it to a constant value, and let's see what happens with the wellbore response. Here we're going to have the pressure in the wellbore, and here time. Okay, so let's start with this. At the beginning, when you're not injecting anything, this is going to be in equilibrium with the column of drilling mud. And let's assume for the moment that, let's say that this value is your pore pressure, and that we start at a value which is somewhere over here. That's the initial PW. And it's not changing because I'm not injecting anything yet. Okay. What would you expect to happen with the wellbore pressure as we start injecting drilling mud into here? The pressure will increase. I guess we all agree with that. The question is, how much will that increase? And according to our equation here, that's going to increase this quantity, the pore pressure plus 2 times the effective horizontal stress plus the tensile strength. That's at the point at which the wellbore is going to develop a tensile fracture and should start at that point leaking drilling mud more than it did before. All right, so I'm going to put that then this equation in here. Let's say that this is 1 sigma h, another sigma h, so now I'm at 2 sigma h, And let's say that from here to here, it's tensile strength of the rock in PSI. Okay. Then what this equation is telling me is that the maximum pressure, or the pressure at which the wellbore is going to break, is going to be limited by this maximum value. So actually this value, we could say it is PB. The pressure is not going to be a lot higher than this, because that's already going to be the limit at which the rock breaks. So at this point, I'm going to start having a hydraulic fracture, or a tensile fracture and then a hydraulic fracture. So the pressure is going to increase. Easily it will go to this value. Notice that at this point, this is where I have the minimum horizontal total stress. So I'm going over that value now, but according to this equation, I can go even further, and there's going to be a point in which the wellbore here is going to start breaking, and as it breaks, it will go to a maximum that we don't know very well how much it's going to be. And what do you think is going to happen after that? Can it continue growing? We said no, because we have an open fracture. Would it continue at the same pressure, or would it decrease? What do you think makes sense for you? What? Level off at this value, at the maximum value? No, look, the injection is still continuing. So we're still injecting, same rate. So it might be a little bit hard to see what's going on here, and what I'm going to say, or we're going to say now, it may not happen all the times, but most times what you will see for a drilling mud is that once you open a fracture, the pressure generally is going to go down, because when you were injecting at this point, the fracture will be generally small, and it will be hard to flow drilling mud through that at a given constant rate. But once the fracture opens up and you get a large fracture, it's going to be much easier for the drilling mud to flow. And because you're injecting at the same rate, the pressure is going to go down, because it doesn't need such a high pressure to flow into the fracture. And the second reason for that is this. Do you remember that we said that a hydraulic fracture, in order to open, should be larger than the minimum stress? Well, in this case, the minimum stress is this one. So if the fracture is open and you're injecting, the pressure for sure has to be higher than this value. So it's going to go down, but how much will it go down? When you are opening a fracture, we're going to see that the fracture is going to open and is going to continue propagating at a pressure which is more or less constant, and is higher than the minimum principal stress. And the pressure needed for that fracture to continue open is called the net pressure. The net pressure is whatever pressure you have in the fracture, usually named as PF, minus the minimum horizontal stress, or in this case, or in general, just the minimum stress. That's going to be the value of this net pressure. Okay, so let's see where we are right now. At this point over here, if we had a wellbore like this one, now this wellbore has a fracture, and we're making a cross section in the open hole section of it. So some of the drilling mud is filtrating through the rock around the wellbore itself, but also I have fluid, in this case drilling mud, that is going into the fracture, is helping the fracture to open up and propagate more, and some of that drilling mud is filtrating also into the rock, but out of the fracture. Okay, so I hope that now you all have this mental image of this wellbore, which is open. It has a hydraulic fracture. Hydraulic fracture is open, and the pressure in the wellbore is larger than the minimum principal stress. That's why it's opening up against the minimum principal stress, and it is opening. All right, so at this point, we're going to shut down injection, and we'll get the injection rate again to 0. Okay, what do you think is going to happen now with the pressure? If you stop injecting, and remember that we're injecting into a rock which is permeable, so the fluid, now the rock is going to press against the rock to close the fracture, and as it does that, the fluid is going to get into here, and the pressure inside is going to decrease, and this is going to increase with a characteristic signature, and as soon as you shut in the pump, this value is going to decrease very quickly, and the value right after you shut in the pumps, that's something called the instantaneous shut-in pressure, or ISIP, and after that, this pressure is going to decrease. All right, how far do you think the pressure is going to decrease? What is the absolute minimum value at which the pressure can go? The pore pressure, right? It cannot go lower than the pore pressure. So in this test, also if you were measuring the pore pressure, you could do this. Usually it's going to take some time, and this is going to approach the pore pressure. Okay. At some point around in this decline curve, we're going to see that there is going to be another characteristic point, which is called the fracture closure pressure, FCP. And that's the value at which the fracture that you created, let me make two schematics here. One for instantaneous shut-in pressure. I'm just going to make half a wellbore. When you shut in the wellbore, you have leak off from the fracture and from the wellbore, but there is no more flow into the fracture because you're not injecting anything. That's at the point at which you shut in the pumps. Between the point that you shut in the pumps and the fracture closure pressure, the fracture is going to close, and at the point at which the fracture closes, now the fracture is closed, you're just going to have mostly leak off from the wellbore and not from the fracture anymore. This is the point, again, at which the fracture closes, and after this, you have just leak off from the wellbore and not from the fracture. And the fracture closure pressure, it's a very useful value because it's going to tell you also what is more or less the minimum principal stress. And that's the main application of this method, to calculate the minimum principal stress out of this data. In this ideal schematic, I made the fracture closure pressure to be almost the same as the minimum principal stress, and that would be the ideal case. But sometimes it may not be exactly like that. And if you measure how long time it takes for this curve to get to the pore pressure, or just to get an idea about how it decreases, you can also calculate permeability of the formation. Yes, Mr. Alismayo.
Observe from our data the fracture closure pressure.
That's what we're going to see exactly right now. After I finish with this example and explanation, we'll see with some data, real data, how we do that. Okay. So for now, just let me tell you that the main difference between before the closure pressure and after closure pressure is that before closure pressure, you have leak off from the fracture and from the well. And after closure pressure, you just have leak off from the well. So that's going to be a quite different trend in how pressure decreases. Okay, well, let's just finish for a moment with this example. And let's, this is basically the leak off test. And when you go over this hump and into this, sometimes it's called the extended leak off test. And this is going to include fracture closure pressure. But sometimes when you're doing this, if you're drilling into a location that probably you don't want to go over all of this, you may just stop it somewhere over here, just knowing that you just got to the breakdown pressure. Actually, this breakdown pressure that you will measure in a leak off test. Now, if you actually do the leak off test and not just calculate it with this equation, then you will get to know what is your actual upper bound for the fracture gradient. So now this value is going to become your fracture gradient. You can measure it. Of course, you know, this is going to be an expensive measurement, but you can do it. And as long as you get to here, then you know that for the rest of your or your section, if it's the same rock, you can get to a fracture gradient as far as this. If you want to continue and measure what is the minimum principal stress, you have to go all over this. And with that, you can also get to calculate what is the value of the minimum principal stress. All right, so let's just finish this example by here, assuming that at this point we ramp up the injection rate again and inject again. what do you think is going to happen with pressure now? It will go up again. But the question is, how far does it go up? So here, there might be two options. Do you think it's going to go to the previous peak? Why not? Because it's already fractured. And if it's already fractured, what do we don't have anymore? Tensile strength. Now we have fractured the wall. We cannot account with this tensile strength of the rock anymore. So in this case, it's going to go over that maximum value. Once you reopen the fracture and continue pumping, probably it's going to come back to the same pressure to which we had before, and it's going to propagate at a given net pressure. All right, so something that we're going to answer later on is what this value is. What is net pressure? And that's going to depend on many things. Principally, it's going to depend on the shape of the fracture, on the stiffness of the rock. It's not going to be the same to open up a soft rock than a stiff rock, and it's going to depend on, of course, on injection rates and the viscosity of the drilling mud. The higher the viscosity of the drilling mud or of a fracturing fluid in general, the higher the pressure is going to be needed to circulate that fluid through a fracture. Here, you know, it appears that I'm making fractures that are several inches wide. But in reality, in real formation, these are going to be actually quite narrow fractures. And flowing fluids through those narrow fractures is going to take quite a bit of energy that's going to be dissipated through viscous losses as you flow the fluid from the wellbore to the tip of the fracture. Okay. Basically, this is a leak-off test, and that would be an ideal leak-off test. The important thing that you remember from here is fracture closure pressure, shut-in pressure, and this pressure, which is the breakdown pressure, which will be the maximum pressure that you attain in the wellbore. Probably you notice that these two are not exactly the same, but this is the one that we calculate just with this formula. In general, the breakdown pressure will be the maximum attainable pressure in the wellbore. It might be a little bit larger than the one you calculate in here, because you need to open up the fracture in order to start getting the fracture outside the near wellbore region. They might be very close, but they, in general, they're not going to be exactly the same. Okay, let me see if I forget anything. Okay, another pressure which is very important is this pressure over here. We said the difference between this and that is net pressure, but here this is going to be the fracture propagation pressure. Let me write down all of these acronyms. So we have breakdown pressure, and here we have fracture propagation pressure. This is the instantaneous shut-in pressure, and last we have fracture closure pressure. Some of these names, they change according to each operator or service company, so they might not be exactly the same, but the mechanics of how it works is the same. The names sometimes they are just not the same. Some other, for example, notation calls this one the leak-off point, the point at which you start to open a fracture and this starts to change, go from a line into something which starts to curve. But I'm fine if you remember all of these that I mentioned before. Okay, so let's see how we do to pick up the fracture closure pressure. It's already 12:42, is that fine? Okay. Okay, here you see an example of this. This is not a leak-off test. This is what we're going to see later. It's a fracture diagnostic test, but it is the same thing, very similar. We have injection rate here in red and surface pressure in blue. If you make a zoom of this data, here now we have injection rate again in red and surface pressure in blue. We see in this particular case that as the injection rate was increased, then it reached a maximum, and then the pressure didn't change much. So this would be the value of the fracture propagation pressure, because pressure is not increasing. As soon as you shut in the wellbore, the first value after the rate is 0, that will be the instantaneous shut-in pressure, which in this case is about 960 psi. And after this point of the shut-in pressure, we can calculate what is the fracture closure pressure with what is called the square root method. And basically what we're going to do is we're going to get this data that you look how it nicely decays. We're going to take as time 0 the shut-in time, and then convert this data into a square root of time. And what you're going to see is something like this, where again time 0 now is shut in. Okay, so time 0 is somewhere over here, which in actual time is 73.6 or 7 minutes, something like that. But now I make that 0, and the time after that, you take a square root of that, and you're going to see something like this. And in this plot, what you see is that after shut-in, pressure goes down very quickly with the square root of time. It also appears to go into a linear trend, but after some point, it starts to deviate from that, which means that after this point, the pressure goes down more slowly. And the reason for that is that there is a transition from flow which goes from like a plane into a porous medium into a wellbore. So in 2D, this is called linear flow, because it appears that the line is that the fluid is going out from a line. If you imagine this, the fracture as a line, and when it goes into here, the fluid goes, it has a point source, and that's why it decays much more slowly. At the point at which you have this change going from a linear trend into something which is not linear, again, with the time as square root of time, that point is a fracture closure pressure. So for this particular test, we see that the fracture closure pressure in terms of surface pressure is 769 psi. And again, you will pick it up by plotting this data after the shut-in, making this square root of time, and then seeing when this trend stops being linear and then goes into something which is not linear. And this is the reason for that. It's a transition of fluid flow. And this is basically what you have to do in problem number 2. So, by the way, the homework associated with this part of the lecture, I already posted it, and it is very easy, and it's due on Friday, okay? I want you to do the homework before Friday, before you go into the Thanksgiving break, just to make sure that that you do it before. Otherwise, it's going to be too much work after that. And the first problem is about a leak-off test, and using the leak-off test to estimate in situ stresses. The second problem is what we just did before, finding this fracture closure pressure. And the third test is about interpreting one of these fracture injection tests. For the fourth one, we'll talk about that on Wednesday. But, okay, in the 2 minutes I have, let me continue with the second one. All right, so we know what is the leak-off test. The leak-off test is done with drilling mud. As I was telling you a minute ago, there is a very similar test, which is called the DFIT test, and it stands for Diagnostic Fracture Initiation Test, which is very similar to the leak-off test, but is done not for drilling, is done for completion. So you may even case your wellbore and run it, and if you've done it for completion, what do you use? Do you use drilling mud? No. Instead of drilling mud, this one is going to use fracturing fluid. And for the DFIT test, the objectives are going to be: one is going to be to measure what is the minimum principal stress, and second is going to be to measure the permeability of the formation. So in order to get to permeability of the formation, it's a little bit more complicated, but the mechanics is a little bit it's similar to the previous one, but there's more advanced methods for that. Okay, so let me just finish with this. One more minute, guys. This one, the DFIT test usually involves small volumes of fluid, usually less than 10 barrels, and also involves small injection rates, particularly taking into account that we are targeting tide formations. In general, less than 3 barrels per minute. And last thing, this one can be done through perforations. Okay, so we'll pick it up here on Wednesday, guys. Have a good day.